So this topic is about very recent work on Contextual Bandits with constraints. So I think this is related to the safe area because we have constraints, so we can view as safety, right? So the key insight from this work is a modular approach with some improved results. This is basically joint work with Alex and Kash and Dylan, and this is new version basically is some improvements over their conference version. And so basically I joined them in this new version. And you can find the new version in archive, and we are on the submission to some journal. Yeah. Okay. So yeah, so this is a theoretical work. So let's directly jump into the setup. So as in the conference version of the SF23, we consider the contextual bandits and with some constraints. Yeah. So we consider online version. So basically, in each round of T, the learner will basically observe a stochastic context. And you can see like a person comes in, right? You want to recommend some medicine to him, and you will choose an action. The action here could be some medicine, right? And you will receive some reward, and also because you have to make a decision, you will suffer some cost. And there are multiple costs. In this talk, I will use M to denote the number of costs or constraints. So this is very simple, right? And the goal here is to maximize the cumulative rewards while minimizing, or maybe, sorry, maybe not minimizing, or maybe, yeah, minimizing the constraint violation. Or in other words, you want to guarantee that on average, this constraint is satisfied. Yeah. And basically, the B here is the total budget, right? There is a threshold you have to below or above the threshold as often as possible. And the sigma here is basically used to flip the sign. Right? So maximizing reward is also equivalent to minimize the regret, right? So the regret basically is the actual performance compared to the optimal performance. Here, because we consider the constraint optimization, so the optimal performance is also a constraint problem. Okay. So the goal here is to minimize the regret and to minimize the constraint violation. And in summary, basically want to make sure both of them grow sublinearly, right? Maybe square of t, right? So some remarks. So this particular formulation of the constraint violation actually allows some degree of the violation, right? So we do not have to guarantee that this constraint is satisfied with high probability at every round. So that is maybe I call that kind of constraint as a strictly safety constraint. But for here, we consider a slightly weaker version of constraint violation. Okay. And it also allows compensation across roles. Okay. And the sigma, the sigma I is basically could be one and negative one, right? The packing and covering. So it's very simple, just flip the sign. Another thing I want to mention is that the reward function and the cost function can be arbitrary, right? It's not necessarily a linear, it could be non-convex from any function class. Okay. Maybe so far so good, right? This is a setup. And how to solve it, right? So in the conference version, basically we can translate or formulate this as some kind of Lagrangian problem or linear programming. So you may wonder, okay, as I said before, right, the R and R, this cost function could be non-convex. How can we relate to a linear function, right? How can we relate to a linear program? The key here is that we change the variable, right? So instead of look at the action, we look at the another decision space. The decision space here is the distribution of policies. Okay. each policy is a deterministic map from the context to action. Basically, you are giving a context, the policy will map it to an action. And the D here is basically a distribution over such policies. And if we look at this kind of decision space, D, we can probably define the expected reward over a D and expected cost over a D, and then the expectation is a linear, right? So it's a linear function. And so we arrive at the linear program at equation 1. Yeah. Okay. So why do we have to do this? Well, you may wonder, okay, why we have to relate to a linear program? Because the key here is that linear program allow us to design an algorithm, right? Why? Because the optimal value of the linear program is related to a max-min value of a Lagrangian. Right?
Okay.
Okay.
I have a question. Sorry for that. So, in the last slides, you mentioned the packing strengths and the covering strengths. So, what's the definition of the packing strength, constraint, and the covering constraint? Yeah.
Oh yeah. Sorry. Yeah, I missed it. So the covering basically says that you can say about the packing is that you have a total budget. You should not go above the budget, right? Because you're packing, right? The covering basically you have to be as minimal as the budget. So just flip. Yeah.
Okay. Thanks.
Yeah, the packing say okay, you should not go above the budget, and the covering say you should be at least this budget.
Yeah. I see.
Yeah.
Thanks for the clarification. Okay.
Sure. Thanks. Please interrupt me if you have any questions.
Okay. Thanks.
Yeah,
please go ahead. Okay.
Sure. Okay, so yeah, we have this kind of LP, right? And the optimal value of the LP is basically, equal to this max-min value of your Lagrangian. And what does this mean? It basically means that we want to find the center point of the Lagrangian, right? Basically, it is the center point of the Lagrangian. And how can we find this, maybe even approximate the center point of the Lagrangian? How to find it, right? And we know that a typical procedure to find a Nash equilibrium or center point is to run a zero-sum game, right? You have a prime algorithms, prime player, and a dual player. And the payoff of the game is Lagrangian. And then that is from the game theory, right? Okay. So this is the whole motivation for us to first convert the problem to LP, and the LP related to the Lagrangian, and Lagrangian can be, the center point of the Lagrangian can be arrived at using some kind of zero-sum game, and the payoff of the game is a Lagrangian function. Okay, so this is the whole point. Okay, so now based on this kind of intuition, we have this kind of in the conference version, basically the authors propose this kind of Lagrangian framework. So you can see we have two algorithms for the prime player and dual player, right? So at each round, so the dual player plays first, and it will choose the decision for the dual player is Lagrangian multiplier lambda, right? So here, right, the dual player will choose the lambda, and the prime player will play the action which will induce this distribution D, right? Okay, so the dual player first choose the action. Oh, sorry, his action is a lambda T, right? Is a Lagrangian multiplier, and within a set. And you can see this is this lambda, this big lambda is basically the enlarged set of the simplex. Right? The eta could be larger than 1, and actually, in certain cases, it is necessary. I will talk about this later. Okay. Now, observing the context and the lambda t, the multiplier, the prime algorithm will choose action. Okay. Now, the action is played, and we incur the cost and the reward. and both of them were passed to diagrams. And now the Lagrange payoff, the payoff in the game is defined as this, right? Guess about like this realization. When you play the action A, you will incur this reward and this amount of cost, and you combine it together as a Lagrange in times in round T, and you will pass this value to the prime algorithm as a reward. That is your prime player's payoff as a reward, and it will also be passed to the dual player as a cost. This is basically a zero-sum game. Yeah. And this Lagrange T, if you take the expectation, it will give you the expected Lagrange, which is the equation we defined in the last slide. Yeah. So this is the whole point. Right? So, okay. Any questions?
Okay, I think this is a very great idea to think about Sephora as a game theory setting. Yeah, very interesting. Okay,
Sure.
so yeah, so there's some game we need to find a balance equilibrium in the game theory the primal player and the dual player. So what we need to do is to control the policy to balance that, right?
Oh yeah, that is exactly my next slide. So,
Okay.
yeah.
Very good. Yeah.
Okay. So as something asked, right? So we have to assume something to arrive at the Nash equilibrium or the saddle point, and basically this is a low regulated dynamics, right? So if the prime algorithms and dual algorithms has a low regulated property, and it can be shown that it will converge to the Nash equilibrium. Yeah. So okay, what is the definition for the regulator for the prime player, and what is the regulator for the dual player? Basically, you can spell like your actual payoff and the optimal payoff, and because for the prime algorithm we are facing the reward, so we have the maximum. This is optimal, and for the dual we are facing cost, so the optimal one should be the minimum. Sorry, this D should be M. The M is basically the number of constraints. So you can like the dual player is choose a multiplier lambda, and you want to choose a lambda to be one such that your total cost is minimized. And the prime player want to choose action or sequence of action such that it will be close to the optimal Lagrange values. Okay, so this is very standard definition. It's not new in this paper. Okay, so this is a prime regret and a dual regret, and we assume that, or this condition we require to be true in this paper for the theorem is that with high probability, there is upper bound on the prime regret and there is upper bound on the dual regret. Okay, and we merge them together and we normalize it. So why we have to divide by eta? Because the whole point here is very simple. Because for in the Lagrange function, we have this lambda I, right? And the lambda I can be as much as eta. So in order to make sure that all the unit is just unit 1, we will divide by eta. Okay. And the R concentration, basically the two terms from Hofding, right? The concentration term typically square of T. So roughly speaking, you can symbol the RT delta, the normalized regret, is roughly square of T in typical cases. Okay, we normalize it because if you do not normalize, the lambda can be, say, very large. Then the unnormalized regret will be very large. It's meaningless, right? So we should normalize it, and our theorem will be related to this normalized regret. You can see about this. This is RT delta is a normalized version of the combined regret from prime, from dual, and from the concentration. So now you can say, well, okay, we have a bound on this RT delta. and what we can see, right?
So
Suppose we have a problem. Okay,
sorry for the interrupting.
sure, no
So
problem.
I just think about wondering, could we decouple the R as a multi-objective like primal and dual and array constraint like three objectives that we need to
Mhm.
optimize. Does that make sense, or I just
Yeah,
intuitively think about
yeah.
it?
So the key intuition for the equation 3 is that the the parameter for the saddle point is basically of this form.
Yeah.
So yeah, so basically you will see that if you have a very large regulator for the prime, very large regulator for the dual, then your approximate saddle point, that approximation is will be worse. So basically,
Mm-hmm.
yeah, that's the whole point. Yeah.
Okay.
Okay.
Okay. Thanks.
Now, okay, suppose we have this kind of very good normalized regret coming from the prime regret, dual regret, and concentration. And then we have this result in the conference version. Uh, suppose that LP we define, and some optimal solution of that LP is strictly feasible. So we have the zeta margin. Zeta is larger than zero. Then we have this kind of result. Basically, say the constraint and the violation, or the constraint and regret is upper bounded by this kind of normalized regret divided by zeta. Yeah. Okay. So this is good, right? So because typically this normalized regret is root t, and basically we arrive at a root t regret for both regret. We have a root t bound for both regret and constraint violations. But the key limitation here is that the stronger assumption that you have to assume that the optimal solution of that LP is strictly feasible, right? It is kind of weird, right? Because in many simple cases and in previous work, even though from a different framework, different algorithms, they can show that with just Slater condition, right? It suffices for the root T regret and constraint violation. The Slater condition basically says that you have a feasible solution. That solution could be suboptimal, right? It should not necessarily be the optimal solution to be strictly feasible. Any solution, if you can find any solution that is strictly feasible, which is a Slater condition, then previous work have shown that even for simple cases, the root T regret is achievable, right? Okay. So this comes to the motivation of this new version. And so basically, can we achieve the same kind of result with a much weaker condition? Get rid of this kind of optimal solution condition. Right? Suppose we only have the Slater condition. Can we still achieve the similar bonds? Okay, so that's the key questions we want to address in this work. Yeah, so this is a very interesting story. So basically, I read the paper of Alex and Klaus and Dylan's paper in the conference version. I found that okay, maybe we can do something. We can do some improvements. And Alex is very nice. So I joined the project, and then we have this new version. So that is the story for this. Okay. So now we have a new meta theorem. This is a new version. So basically, I joined the project and make some contribution. The result is very simple. So instead of strictly feasible optimal solution, so if there is any solution of that LP is strictly feasible, and then we have this result. So basically, the constraint and the regret is upper bounded by the same order. And also for the zeta zero. So if you do not find any strictly feasible solution, right? If you do not find any strictly feasible solution, the zeta is zero. And you still have this some weaker guarantee. Okay, so you can see if the R is a root T in the first case, your regret is root T, right? And in the second case, your regret would be T to the power 3/4. Right? Okay, so this is a dual theorem. Okay, so This is achieved by a brand new analysis. It's totally different from their previous analysis. And in fact, in the strictly feasible case, the Slater condition case, we can even achieve zero constraint violation. Okay, we have included in the paper. It's very simple. You just tune this kind of budget a little bit, you can achieve it. Okay, so I will briefly talk about the proof because I really like this proof, and I think the proof is generalizable, so it can be generalized to many cases. And the proof is very simple. Okay, so this proof. The first step, very standard. So every step of the proof is very standard. I do not want to claim everything new here. We just do a very nice, some kind of combination or whatever. So yeah, but I still like this proof. Okay. The first step is basically say, okay, the average play of the prime and the dual player converge to an approximate saddle point. And the approximation ratio of the approximation parameter is related to this kind of normalized regret. Yeah. Okay. So what does it mean by approximate saddle point? Okay. So basically it says that okay, you satisfy this kind of two inequalities, right? Okay. So this is the definition for the saddle point, approximate saddle point. And how can we show this? I would say this is somehow routine analysis, because it's essentially from the very classical paper, the first paper on this kind of low regret dynamics. Yeah. There is slight difference because in this classical paper, they consider determining there is no randomness, but in our bandit case, we have randomness. The reward relation is sample from a distribution. So you have to take care of the concentration. So that's the reason why we have the concentration in this normalized regret. Okay. Okay. Now, we have shown that this average play will converge to a saddle point. Can we utilize some kind of existing properties of a saddle point to directly give us the result of regret and constraint violation, right? We do not want to do a specific analysis for this particular problem because it's not necessary, right? So if we have already shown that this average play converges to a saddle point or Nash equivalent, can we use some kind of existing results to give us the regret and the constraint violation? And yes, this is the main lemma we use in this paper. So it says that if the d prime lambda prime is a saddle point, and it directly satisfies the following three properties. The first one, the d prime, the average play, is very close to any RD by this, by this 2V, by this kind of approximation ratio. Okay. So this will be used to directly give us a regret because you can say the regret is related to this difference of RD star minus RD prime, right? And the difference is 2 nu. And the 2 nu is related to the normalized regret. And the second one, it says that, okay, the D prime will satisfy this condition. The D prime will satisfy this condition. Okay? What does it mean? What does it mean? It means that if you look at this third term, right, it is quite related to the constraint violation. And you can directly massage this term to give you the constraint violation. The third property, if the Slater condition holds, you have another property or equation or inequality for this term. And this term will also directly give you the constraint violation. Because this one is basically roughly equal to the constraint violation. Right. There is a difference of 1 over t, right? You can times t and then you recover the constraint violation. So you can see, right? We have the saddle point, and the first property will give us a reward or the regret. The second property will give us the constraint violation for general cases, even though you do not have the Slater condition. And the third property will give you the constraint violation for the Slater condition case. Then we are done, right? So if we have this lemma, and then we are done, basically. And how can we arrive at this lemma? This lemma is basically some kind of a variance of some existing work. Okay. So we do maybe a nice massage of all the results to make it as clean as possible, and we arrive at this lemma. And with this lemma in hand, we can directly give the regret and the constraint violation. How? So remember, the approximation ratio is a loop and is on this order. So by property 1, we know that the regret is roughly on the t times this kind of average, the RD star minus RD d bar, right? And the difference of these two, we know that d bar is basically a settle point by step 1, right? And so basically the difference of these two is on the order of t times nu. T times nu is basically eta times r. Okay. So for constraint violation, we have two cases. If the data equal to 0, though, then by property 2, we have this kind of, the key here is that we want to bound this third term, right? And we know that reward is upper bounded by 1, so we can basically replace this one by -1, 1, and move to on the right hand side. And then basically we have this kind of thing, right? We have this kind of, that's the reason why we have 2 nu plus 1. Right, this 1 comes from this naive bound on this term. Okay, so that's the key reason why for the general cases we have a reverse rate of performance, because this 1 we have this t over eta, and this is the problem actually. Okay, due to this problem we have to choose a very larger eta, and because you have to choose a larger eta to cancel this t, right? Because it's larger eta, then you have to pay something, because you have a linear term of eta here. So this is the reason why for the general cases we have a reverse performance. But for the Slater condition case, you do not have this t over eta. You only have this kind of r and eta times r. So that's the reason why you can achieve root t regret. Okay, so I like this proof because it's very simple, and also it will give you the insight why there is a difference between the general case and the Slater condition. And yeah, that's a proof. Okay, so basically it's maybe just 1 page. It's very simple. And any questions regarding the proof? I think the key part is this lemma. Yeah, I do believe that this lemma can be applied to many other cases.
Yeah, I just wondering, could we deploy this for like multi-agent? How can we do that? Like say multi-agent optimization in that case?
Yeah. Yeah, I think that's a good question. So I think if you consider this kind of standard feeder learning setting for bandits, yeah. I have been thinking about that a lot because yeah, I'm not sure whether there's some work on this kind of feeder learning of the constraint bandits. I think the tricky question here is that how you define the constraint. Is it define the constraint as an individual on each agent, or it is a constraint on a global constraint? Yeah, I have been spending a little bit time on that problem, but I think I gave up. I do not have a clear formulation of that problem. So yeah,
Okay.
yeah,
Okay,
okay.
thanks.
Yeah, okay. Okay, so this is the proof. Okay, so what would be the next one? I think we have 20 minutes, right? Okay, so let me discuss some kind of related work and a concurrent work. By concurrent work, basically means that when we work on this new version during the last 2 months, I think there is some kind of loops or submissions, and also some kind of this year's core paper which start very similar problems. So we want to include them to discuss. And I also want to relate this new framework with previous one. Yeah. I will discuss from 3 aspects. The first one is that what would be the dependence on the number of constraints, right? So the n. So in our work, we have this kind of, so in simple, let's say very simple constraint multi-bandits. In a simple case, we have this kind of square root log. But in previous work, the dependence is square root of n. So basically, you can see that there's a huge difference, right? This is the first aspect that I want to discuss. The second aspect is that, okay, you have a framework. So we have a framework. This kind of Lagrange prime and dual. We say that, okay, if the prime and dual have the low regret property, we have such bound. It's a very natural question to ask is that, does this framework include the previous algorithm as a special case, right? Yes, indeed. In certain cases, previous algorithms can be viewed as a specific instance of our general framework. That is the second point I want to make. I will discuss in details later. And the third point I want to discuss is that in our current framework, if you remember, the learning rate, the eta, will depend on the Slater parameter zeta. So we have to know the zeta in advance to choose the learning rate, right? So some confounded work actually try to solve the problem and say, okay, suppose we do not know the Slater condition, the parameter in advance, can we still achieve some kind of root T regret? So we want to be adaptive, right? We do not want to know the zeta in advance. Okay, so let's discuss them one by one. The dependence on number of constraints. Let's first look at the very simple non-contextual case, like the simple multi-bandit. In our algorithms, you can choose the dual player as the H, right? Or you can spell online mirror descent. We can have this kind of square root log n, right? This is from the regret guarantee from the H. So this is in sharp contrast to the previous one, right? Where the dependence is on the square root n. So the key difference here is that in the previous work, they will use gradient descent as a dual player. But in our framework, we can choose the mirror descent. And we know that this is well known, right? Over the simplex decision domain, you should use mirror descent because it will give you a tighter dependence on the dimension. Okay. Okay, you may wonder, okay, why can we change your previous work? Say, instead of using gradient descent in their framework, can we use mirror descent in their proposed algorithms, right? To the best of our knowledge, it's not clear because their analysis will rely heavily on the choice of the dual algorithms. Okay. So the second case is contextual case, right? Currently, we do not have a sharper weight. We also have this kind of square root n. So it's kind of open, right? It's kind of open, right? Can we improve on this? If for the contextual case, can we achieve log? I think we made some kind of preliminary results for some kind of specific case. If your constant function reward function is linear, we do think we can achieve log. But for general cases, we do not have any results. Okay. The second aspect, we want to recover the previous algorithm as a special case. So say let's consider the non-contextual case as an illustration, right? So in this case, our prime algorithm would be the exp3.p, the high probability version of the exp3, and for the prime. And in a simple, this is the adversary learning algorithm, right? But in the simple cases, previous algorithm will just use UCB as the prime. So basically, like previous work, they will use UCB as a prime and gradient descent as a dual, and plus a very tailored analysis. They can show this kind of root T bonds. So a question here to ask is that, can we show that their prime algorithm and dual algorithm satisfy the assumption we require for our framework? And then we can directly use our meta sim to give the performance guarantee, right? So yes, because we can show that both of their prime and dual satisfy the assumption. And then we can directly utilize the meta sim to give the performance, right? So there is one subtlety. For multiple constraints, if you wanted to follow this approach, we will sacrifice even worse dependence on the number of constraints. I want to mention that in both of these two works, they also rely on very similar the tool, the lemma from our key lemma. So yeah, but they use it as a very tailored analysis rather than this kind of low regret dynamics and a setup point. So basically, they do not explicitly view as a setup point optimization. The last aspect I want to discuss is that suppose we do not know the Slater condition, the Slater parameter in advance, can we still achieve some performance bound, right? Yes, there are two very recent concurrent work. We divide into two categories. The first category is also based on the low regret dynamics. But in order to be adaptive, the key insight from this paper is that the prime regret and dual regret should not just be low regret. So basically, I think their title is low regret is not enough. Your performance or your prime algorithms and dual algorithms should also be weakly adaptive. So this is they define this kind of in their paper. So with this kind of property, they can show the same bounds, but the scaling, the dependence on the number of the depends on the zeta and depends on the number of constraints are both worse. So remember, in our bound, the dependency is 1 over zeta, but now they become 1 over zeta squared, and their dependence on the number of constraints is even worse. Is m to the cube, is the cubic of m. Okay. So it's not that satisfying, right? And the second approach, which is from the recent code paper, this is based on the Lyapunov-Drift approach. The key insight here is that you can relate to the constraint violation to a virtual Q length. And with this kind of a new approach, you can show that it can be adaptive, but also at a cost. The cost is that the dependence on the zeta is no longer 1 over zeta, it's 1 over zeta squared. It is worse, right? And also in this signal paper, they do not consider multiple constraint case. They only consider single constraint. So it's unclear what will be the dependence on the number of constraints in the signal paper. So electric question is, can we improve on this, right? Can we achieve adaptivity, but also a very nice dependence on zeta and dependence on the number of constraints, right? Okay, so yeah, I think I will make the conclusion at this moment. So basically, we have shown that we can achieve the root T bounds on a much weaker assumption. and it includes the previous argument special case, and it has the advantage over previous work on the dependence on the number of constraints. And future work, can we improve on the dependence on the number of constraints? Can we start the limit of the cost of adaptivity? Of course, a very natural question is can we generalize to IO? I think generalizing to IO is also straightforward. You basically use some kind of prime algorithm for RL and prime algorithm for the dual is basically the hitch, and the prime you can use some kind of no regret adversary learning for RL. You can also have basically for the same lemma, the same proof, you can have this result. Okay, so I think that's all for my talk. Yeah.
Okay. Okay, thanks.
Sure.
Thanks, Professor Zhao. So I was wondering, do you have some experiment results like for this algorithm and this thread?
Yeah, unfortunately, we do not have any experience. So yeah, we do not run any simulations. Yeah.
Okay.
Yeah, I think even in the conference version, they do not have any experiments. Yeah.
Okay. So I want to know if we use this setting like consider CFR as a commissary setting. So in that case, how the performance? So is it better than the regular CFR methods like Lagrangian, the simple Lagrangian methods? So
Yeah.
and
Yeah, I do think they are not comparable because I think in typical safe RL, they require that your constraint violation is basically, you do not have any constraint violation, or you guarantee that you will satisfy the constraint, the safety constraint with high probability, right? So basically, when you make the decision at each one, yeah, there are many there's many theoretical study of safe RL, safe bandits. The typical procedure, as far as I know, is that when you make the decision, you first construct some kind of a proper set, and that set is based on your previous history data, and make sure that that data will contain only the safety action, right? And then you will choose among that set to make the decision. So this will guarantee that you will not violate the constraints. But in this paper, we do allow this violation of constraints. So it's a different setup. So you may wonder, okay, so what would be the application scenarios of this formulation, right? You basically maybe you have some energy consumption, you have some fairness constraints, you can use this kind of formulation. But if you have some kind of strictly safety constraint, then this formulation is not sufficient.
Okay, thanks.
Yeah.
So, any question from the audience? I think that's it's our theoretical talk.
Yeah, I think
though.
it's
Yeah.
it's a purely theoretical paper.
Yeah. Okay. Joseph. Hello.
Yes.
Yeah.
So thanks a lot for the talk. Yeah, quite theoretical, but yeah, I think very useful in the same time. For we have recording of this, so if it's fine for you, we can share this later on
Sure.
a YouTube channel so people can watch it. I guess, as you mentioned, a lot of people cannot join because of the timing of the talk.
Sure.
If it's fine with you, we can upload this later on our channel, and also people can have a look there.
Sure.
Okay, so is there any questions from the audience, or should we call it today? Yeah, I think there are no other questions. So yeah, then I think we can close. Thank you both, Shangli and Professor Zhou, for joining.
Yeah, thanks.
And yeah, until the next time, so probably in a month or something, we'll probably have another talk. We'll announce that on the Safe Reinforcement Learning online seminar mailing list. So please join the mailing list if you're interested in following more of these talks. And by then, yeah, wish you good night in China and good morning in America and Europe. Now we are in the evening, so have a nice time, everyone.
Okay.
Bye bye.
Thanks.
Bye bye.
Bye. Bye.